world can be represented as a complex networks. So we have a dedicated research group at IIIT Kottayam for analyzing such complex systems in the real world. You can just explore just Google Network Science Research Group IIIT Kottayam. Then you can go to the website of our research group. Our main research interests are in analyzing the robustness of complex networks, brain networks, epidemic dynamics, climate networks, and so on. As part of these works, we have collaborations with several foreign universities. And specifically, I am working on robustness of complex networks. As part of this, we have the collaboration with the Networks University of Parma, Italy. Then if anyone have the interest in studying the analyzing robustness of complex networks or any kind of complex systems in the real world, you can just mail Dr. Divya Sindilega. She is the head of our network science research group. You can contact us. We have different funding opportunities, funding projects, different internships are there. So if you are interested, you can contact us. Okay, then coming to our today's lecture. uh, Today I want to give a brief introduction about machine learning. What is machine learning? Then we will discuss different machine learning paradigms. Among them, we will focus on more focused on supervised machine learning algorithms such as regression and classification. Then finally, we will conclude how we will evaluate these different techniques. Evaluation, what are the different evaluation measures to analyze the quality of these models, machine learning models. Okay. Then what is machine learning? In the case of human can learn from past experiences. Based on this past experience, he can make its own or his or her own decisions, right? Suppose if we gave this picture and asked him, what is this object? Then suddenly he will recollect his information. He already know from the past experience what are he already knows different vehicles, the images of vehicle. Then he will recollect his informations and suddenly he will answer it is a car, right? He got this answer based on his past experiences. Through his past experiences, he gained the knowledge about how these vehicles, how the car looks like, how the bike, how the bus looks like. Based on he already knew. So based on this information, he replied that the this picture, this object is similar to car. Then if we ask the same question to Tarzan, Tarzan is an animation character living in the forest. If we ask the same question, what is this object to Tarzan, he may not be able to answer because he knows only the animals like elephant, lion, tiger, right? Maybe based on his experience, he will look into this object and analyze the shape of the object. Maybe his answer may be this is an elephant, right? But if we teach him by providing the pictures of different vehicles and provided that this is a car, this is a bike, this is a bus, and he learned from these pictures and identified the different vehicles, how the different vehicles look like, then he may be able to answer this is a car. If we teach him by providing the pictures of different vehicles and providing the labels of each of these vehicles, then he may be able to answer. Otherwise, he may not be able to answer because he don't know any information about the vehicles. Okay. Then, what about a machine? Actually, the machine follows instructions, right? Machine can follow instructions provided by the human. Then it cannot make decisions of its own because machine can follow the instruction just one by one instructions provided by the human being. It cannot take decisions of its own. Then we can ask the machine to perform the arithmetic operations such as addition, multiplication, division, and we can also we can ask the machine to perform some comparisons between the numbers, comparison between the strings. We can ask the machine to print a particular document, and we can ask him to plot a chart, right? We can ask machine to do several tasks, and machines will do these tasks based on some instructions, some sequence of instructions, which is known as program, right? So then, but we want a machine to act like a human, right? From just the machine that follows the instruction provided by the human, we want a machine to act like a the machine to act like a human, to identify the objects, to predict the price in the future, and to understand the natural languages and correct the grammar. If we give some sentences, see, if we give some paragraph, the machine should be able to identify or correct the grammars like human, and the machine should be able to recognize the faces of different humans. So what do we do? Just like what did to human, we need to provide some experiences to the machine. Then we can think that based on the experiences we provided to the machine can learn something. Then based on the learning experiences, machine can do something just like human. Okay, so the first step is to provide some experiences to the machine. Experiences in the form of some kind of information, some kind of data. We can provide something to the machine. Using that, machine should act like a human. Then for that, we can first of all we have the machine. Then we will provide some data. Okay, and we can call it as a training data set. That means the data set used to train or learn the machine. Then, so we first need to provide the training data set to the machine. Then using this data set, we will devise some algorithms or executes programs on this data based on the which task we need to perform. Based on the underlying target task, some algorithms, some particular programs are executed on this data set. Then using these programs, using this model, we will identify the rules using this data set and model, and identify or extract some required patterns available in this data set, and find out some relationship between this data set. Okay, then so that after getting rules, patterns, relationships, machine can act like a human. Okay, so by providing some experiences in the form of data set, machine analyzes or executes some algorithms, some programs for finding out some patterns, some rules, some relationship. Then the machine can act like a human. Clear? Then, in summary, what is machine learning? We have a machine learning problem, and based on that problem, we will create appropriate data set. Then we perform some computation to learn some rules, patterns, relationship. Then machine will give output the decisions, just like human. Then based on the task or availability of the based on the data, the machine learning paradigms, there are mainly three paradigms are there: supervised learning, unsupervised learning, and reinforcement learning. Coming to supervised learning, we have known input data, which is known as input variable, independent variables or features. And also we know the output variables, which is known as labels or targets. So we know the inputs and their corresponding output. And using this data, we want to find out this function that maps from this input to output. And this function we want to identify. This function is unknown to us. So using this known input and output, we want to map from input to output. We want to identify the function that maps from input to output. Then here we have the data, and all these data are labeled. Why it is known as labeled? Because for each input they are providing what kind that animal, right? So this is owl, this is fox, this is fox, this is owl. So we have that output data, we have the labeled data. And using these labeled data, the machine learning model can perform some training, and the model should be able to identify the owl and fox separately. Here we are using these labeled data. Label in the sense for each category we have the output. Then using this labeled data, machine learning should be able to identify which one is owl and which one is fox. If we provide a new picture, the model should be able to predict whether that new image is owl or fox. Okay. Then and this is another one. Here we have different. The data set consists of different dog species. Using the machine learning model, it will learn something. Then, after giving the test data, the model should be predict the species of each of these data. It should be able to predict the species of each of these test data. Then the next one is sometimes we require to predict some real world numbers, some real numbers, like predicting the price of a house. And we can predict the house price based on the already available data set. Like for each house we know the price based on the size, some other kind of features, number of rooms, number of the square feet of the house, age of the house. Using these features we know the price of each of this house, and using these data are we able to predict the price of this house. And next one, we have the set of male, and also we already know each of these males, whether this male is sperm, or this is an inbox male, or this is a sperm male. We already know the classification of each of these male, and based on these data we should be able to classify whether the new male come to inbox male or sperm folder. Okay, so classification and regression problems are supervised. These are the till now we discussed different examples, right? So classification and regression problems are supervised machine learning technique, because the decision of these problems are depending on the characteristics of ground truth labels. We have the labeled data set, so decision will be depending on the characteristics of these labeled data set, and which these labeled data set can be defined as the experience we are giving to the machine, right? We are providing the experiences to the machine in the form of labeled data set. So in each of the supervised learning we provided the labeled data set. We are providing the output of each of these data set. Based on that we can classify them, or we can predict some real values, some real numbers. This is known as regression. Predicting the some real numbers is known as regression. And also we can classify whether it is the newly coming mail is inbox mail or spam folder mail. We can classify them. Then coming to unsupervised learning. Coming to unsupervised learning, we have unlabeled data. We don't know whether each of these one is owl or fox. We have just like we only have a set of images, and this is known as unlabeled data. But coming to supervised learning, we have labels. We have the outputs for each data set, right? But here on unsupervised learning, we have no label for each of this data set. So using this unlabeled data set, model should identify whether the newly coming image is owl or fox. Then how machine will learn the patterns from these unlabeled data set. They will identify the similar kind of images and identify the newly coming image is similar to this one and it can be the owl. And similarly, identify the fox patterns and identify this newly coming one is fox or not. Okay, so tomorrow's section we will discuss about unsupervised learning. Then another example is, suppose we give the some fruits to the kid and ask him to classify these fruits. But he does not know the label, whether it is apple or orange, he does not know. What he will do? Based on the colors, based on the shape, they will categorize these fruits. Then finally he will get two class of fruits. One is apple and one is orange. Even if he does not know the apples or orange, but he will be able to classify them based on the shape, color, some features, right? This is an example for unsupervised learning. That means we are clustering, we are grouping our available data set. Then coming to reinforcement learning. Here, this is the third one. Here we have an agent. Agent want to take some decisions by some actions through some interactions with the environment, and the agent will get some feedback in terms of reward or penalty. And this reward or penalty will indicate how far or how far or how close he is to the goal of the model. This is the reinforcement learning. And these are the semi-supervised, semi-supervised, and reinforcement learning are the three main categories. And the use cases for reinforcement learning are robotics, games, and recommendation system. And the another category is semi-supervised learning. In semi-supervised learning, we have both labeled data and unlabeled data. We have small amount of labeled data and large amount of unlabeled data. And we will provide both these labeled and unlabeled data to the machine learning model. The machine learning model try to label all the data set, and which is known as pseudo labeled data set. Okay, using labeled the small amount of labeled data set, machine learning model will label these unlabeled data, and the resulting data set is known as pseudo labeled data set. Then using this pseudo labeled data set, machine learning model trained and will try to predict whether the newly coming fruit is either apple or pineapple. Okay, that means the trained machine learning model will able to identify the group just like human, and that means the first group 1 will be labeled as apples and group 2 will be labeled as pineapple. And another kind of another kind of machine learning paradigm is self-supervised learning. There are several different variations nowadays, but these are the main categories: supervised, unsupervised, and reinforcement learning. In supervised learning, we are providing some labeled data, input data along with their labels. Using some training algorithm, model should be able to predict whether which category is this animal or not, or the model should be able to predict some real numbers, some real categories. Okay. Then coming to unsupervised learning, we have mix of data, but the labels of these data are not provided. Then model will perform some training algorithm and able to identify the similar patterns. Based on this pattern, they will form some clusters of similar object. Then coming to reinforcement learning, here we have an agent will perform take actions by interaction with environment, and agent will get some feedback in the form of reward or penalty. This based on this reward and penalty, agent will perform some actions in order to reach to the goal. Okay. um, then next we are moving to the first supervised learning algorithm, regression. I hope it is visible, right?
Yes, visible, ma'am.
Thank you. Then we are moving to the first supervised learning algorithm, regression. As we already discussed, so in supervised learning, we have the data with the labeled data, and using these labeled data, we want to identify or predict or classify the newly coming data, right? And linear regression means we are continuously regression means we want to predict some real values in the future. Okay. And one simple one is simple linear regression. In simple linear regression, it is a method to understand the relationship between the two variables. We have only two variables. For example, we want to predict the salary of a human based on the experience or based on the working hours. We want to predict the salary, and we want to predict the annual salary based on the years of work experience. Okay. And this variable we want to infer or we want to predict based on some another variable. Okay. So variable we want to predict is known as dependent variable, and variable we used is known as independent variable. Okay. So here in this example, the annual salary will be the dependent variable, and the years of work experience will be the independent variable, because this annual salary is decided based on the years of work experience. So this annual salary can be considered as the dependent variable, and the years of work experience is considered as the independent variable. Clear? Then the next example is predicting house prices. Here we want to predict the house price based on size of the house. That means house price depending on size of the house. So the dependent variable is price of the house, and independent variable is size of the house. But this is not the actual case. In the house price can depending on multiple factors, like the in which year that house was constructed, and whether the swimming pool is available or not, a number of bathtubs or bathrooms, and square feet of the house. Based on these factors, we can predict the house price. That means the house price depending on multiple features like square feet, availability of swimming pool, number of rooms, the which year it was constructed. So this kind of predictions is known as multiple linear regression, because here the output depending on multiple features. In the previous one, simple linear regression, the output depends only on one feature. That is why it is known as simple linear regression. Here we have only two variables, and this dependent variable will be predicted from only one independent features. Here we have only one feature. Then, how do we calculate a simple linear regression? For that, firstly, we required some data, right? And this is the data of 10 houses. Here we have house size and its corresponding house price. Then the next step is to, are we able to model these data? Okay, for these model, these data can be represented as a just like y, just like a line, like y is equal to bx plus a, and here y is the house price, which is our independent dependent variable, the variable we want to predict house price y, and x is the house size, our dependent variable. Yeah, house price is the variable we want to predict based on the independent variable house size x. And using this equation, are we able to model these data? Okay, then how? For that, we can use linear regression, simple linear regression. Firstly, we can visualize these data using scatter plot. In scatter plot, the x-axis shows house size, our independent variable, and on the y-axis we can show house price, the dependent variable, and each of these data point is the house. Each of these data point indicates a house with a respective house size and house price. Then we want to model we are trying to find out a model that is best suitable to these data set. For that, we are finding out a line that is very close to, or that is very able to model these points, all these points. Okay, and the line can be drawn, any line can we can draw, right? But the actual model will not be the random one. Then how can we decide which line is the best one that completely describe this data set? Okay, for that we are identifying the difference between these actual data points and the predicted value in this line. That means distance between the actual point and the line itself. Okay, and this line, this red colored line is called error. And the goal is to find out the regression line, find out the line can be drawn randomly. But we need the line, we need the regression line that minimizes these error. These differences can be considered as an error. The difference between the actual point and this point, from this point, the predicted point. These points in this line is known as predicted points. Okay, so this red color length of this red line indicates the difference between the actual point and points in the line. And if we take the sum of all these length of this red line, we will get the total error. So our goal is to find the regression line that minimizes this error. These distances should be minimum. Some of these distances should be minimum. Then how can we identify such best regression line? For that, we need to identify the parameters of this line b and a. The regression line is represented by the equation y is equal to bx plus a. This is the format for line, equation for the line. Then we need to find out the parameter A and B that best suited for this regression line. Then what this B? B is the slope of the term, slope of this line. What the slope indicate? Slope of the line, best fit line indicate how much the dependent variable, here the dependent variable is house price, how much the house prices change if we change the house size one by 1 unit. If we change the house size by 1 unit, then what change will occur in the house price? For example, if the slope is 5, means if we change 1 unit, if we increase the x-axis by 1 unit, then the value of y increases will be 5. Okay, if the slope is 5 means if we change the x-axis, if we increase the x-axis by 1 unit, then y will also change by 5 unit. That 5 is known as slope. Okay, so in our example, if we change the house size by 1 unit, then how much amount of changes will occur in the house price? This is the term B. Okay, then coming to A. A is the intercept on y-axis. It represents the predicted value of y when x is equal to 0. Okay, intercept is the point on the y-axis when x becomes 0. In this example, when the house size is 0, what will be the value of house price? Of course, in real scenario, house having size equal to 0 does not exist, but mathematical models can be used to represent the real world scenarios. In this example, A indicates the intercept on the y-axis. Okay. Then, so the simple linear regression, our model is defined by regression line. We have a regression line with a, which is defined by the slope B and intercept A. Okay. Then, if our intercept is 100, that means if the x-axis is 0, then the y value will be 100. Then we can simply put it in the terms of A. Then, if we increase the x-axis by 1 unit, that means if we increase from 1 to 2, then what change will occur in y-axis? If we increase from 1 to 2, then the y value will be changing from 150 to 200. That means the change of amount is 50. 50 units will be changed, or 50 units will be increased. The slope will be, so the value of b will be 50. Y is equal to 50x plus 100. This is the equation for this line. In this way, we want to identify which line, which regression line is the best one to our model. That means which regression line will reduce the total error. Okay. Then using some mathematical statistical equations, we can calculate the value of B and A from the available set of data. But rather than directly computing this formula, we often estimate the parameters such as slope and intercept by minimizing a cost function. Here, I will discuss about the cost function, and using that cost function should be minimized. For that, we have some optimization technique which is known as gradient descendant. Then, why do we need a cost function? Because as we already discussed, for the data points, we can draw multiple lines, multiple regression lines we can draw, right? But different regression line will produces different prediction errors. So we need a measure, we need a method to compare these different regression lines. We need a numerical measure to compare these models. So the best model will be the one with the lowest cost. So what will be that cost? In our regression line, our goal is to minimize the error. If we identified a regression line, then our goal is to minimize the error between the actual point and the predicted point, right? So we want to identify the line that have minimum error. Then in linear regression, the best fit line is the straight line that accurately represent the relationship between these independent variable and the dependent variable. That one is the best fit line. It is a line that minimizes the difference between the actual data point and the predicted value from the model. Then how can we calculate such best fit line? And difference between these actual point and the predicted point, that can be known as residuals. Okay, this distance can be considered as the residuals. This residuals measures how far a data point from the regression line. This yellow line is the regression line. Then this red line, it is known as residuals. It will give the idea about how far our data point from this regression line. And how can we calculate the residuals? Residual will be the difference between the actual data point. This green colored one, blue colored one is the actual data point. It is represented by Y. And the predicted data value, it is represented by Y cap. The point in the regression line is known as predicted Y value. So residual is calculated by the difference between the actual data value and predicted data value. Okay, then what are the interpretations? What is the meaning of residual equal to 0? Residual equal to 0 means the perfect prediction. This point, the actual point will be on the regression line. Actual point, actual point and predicted point will be on the regression line. So the difference will be 0. Okay, residual equal to 0 means we got the perfect prediction. And what is the meaning of positive residual? If we take this difference between actual and predicted value, then if it is positive means model underestimates the value. That means this actual minus predicted is positive means actual is high, right? So the model regression line underestimates the value. So in this case the value will be positive. But if the actual value is below the regression line, that means the residual will be negative. When the residual will be negative, it indicates the regression line overestimates the actual data point. Okay, so residual equal to 0 means we got the perfect prediction. There is no difference between actual and predicted value. And it is positive means model, positive means these top lines, the points that are falling on the top, on the above the regression line. Okay, in that cases actual points will be high. So if you take the differences between actual and predicted, the value will be positive. The positive residual means the model, the yellow line, underestimates the actual point, and the negative residual means the model overestimates the values. Okay, then mathematically, you will obtain the best fit line by minimizing the sum of these residuals. Okay, and that is known as cost function. Okay, in our example, mean squared error will be considered as the cost function. How it is defined? Mean square is the average of difference between the actual point and predicted point and taking their square. That means mean square error is the average of square differences between the actual point and predicted point. This is the cost function, and cost function helps to work out the optimal value of B and A. Our aim is to find out the best regression line, right? Then for that best regression line, we required what will be the slope of that line and what will be the intercept. Then only we can define that line. Then in order to find out such optimal value, we need a cost function, and here the cost function is defined by the average of square differences between the actual data point and predicted data point. Here yi is the actual point, yi cap is the predicted point. Taking their differences, it is known as residual, and we take the square of this residual and take the sum of all these squared residuals, then take the average. N is the number of data points. Then by squaring, in the previous slides we discussed that residual can be 0, positive or negative. By squaring, the value of mean square error will be always will be positive. Okay, then why we are by another advantage of squaring will be larger errors are penalized more due to the squaring. That means if the error is 2, after squaring it will be 4, but if our error is 10, it is large value, then after squaring it will be 100, it will get more significance in this cost function. And lower cost indicate if this value is less, indicate the model performs well. And cost is equal to 0, mean square error is 0 implies we will get the perfect prediction. That means the difference between this actual and predicted will be 0. Then after calculating we will get the mean square error 0. Okay. Yes. Any clarification? Is my screen visible?
Now it's not. It's not visible right now, ma'am. Yes, it's okay. Fine now, ma'am.
Yeah. Then our objective of linear regression is find out the values of slope and intercept that minimizes the cost function. In our example, mean square error. Okay. Then these parameters can be determined using the optimization function gradient descendant method. Using this gradient descendant method, the value for the cost function is minimum. Our objective is find out the slope and intercept of best regression line. For that, we can use gradient descendant method, which will help to identify the cost function to minimum, which will helps to identify the parameters such a way that the cost function will be minimum. Here in linear regression, our cost function is mean square error. Then how the gradient descendant will work? Gradient descendant is an iterative optimization algorithm that optimizes the cost function. Here we can consider it as the objective function. We want to minimize this cost function. Then in order to find out this optimal solution, we need to reduce the cost function for all the data points. And this is done by updating the values of coefficients B and A. That means updating the coefficients, slope and intercept iteratively until we get a optimal solution for the linear function. Here, this is the mean square error. Okay, and it can be considered as the cost function J. The cost function J is defined in terms of A and B, slope and intercept, which is equal to average of squared differences between the actual and predicted values. Then why we add, in the previous example we discussed that mean square is 1 by n, right? Why we add, coming to cost function, why we add 1 by 2? Actually this is only for the mathematical convenience, because when we perform the differentiation, d by d theta of x, the differentiation of x raised to n will be n into x raised to n minus 1, right? So differentiation of x square will be 2 into x raised to 2 minus 1. The same way d by d theta of y minus y cap the all square will be 2 into y minus y cap, right? So in order to cancel these two, we can add 1 by 2. This is only for the mathematical convenience. Okay. Then so this is our cost function J. Then y cap is the predicted value, and it is defined as y is equal to bx plus a. So ith predicted value will be equal to b into ith observation plus a, and substitute this value, and this is the cost function after substitution. Then objective is to minimize this cost function with slope and intercept. Okay, this is the objective, minimizing the cost function and identify the slope and intercept of that cost function. Okay, then how do we find the values of a and b that gives this minimum cost? For that we can use gradient descendant. And what is the idea of gradient descendant? Suppose imagine that you are standing on the hill. Okay, then your goal is to reach the lowest point in the hill. Then how can we check? How can we do that? Check the current. You are in the current here. Suppose you check the current location. Then check the what will be the slope, whether it is downhill or uphill. If it is downhill, you can move. Again check the slope. Then again you can move downward direction and repeat until you reach the bottom. This is the main scenarios or main idea behind the gradient descendant algorithm. It is an iteratively running optimization algorithm. Okay. Then what the working principle is, initialize the b and a with a random value, some any random values. Then compute the cost function. Cost function is j of ab is equal to 1 by 2 and sigma I is equal to 1 to n yi minus bxi plus a the all square. That means average of differences between yi minus the actual the predicted value. Okay, then compute the cost function, then calculate the gradient. Gradient means slope of the cost function. Okay, then in that it is calculated by dou j by dou a and dou j by dou b. Okay, then dou j by dou a, this is the partial differentiation. That means dou j by dou a means gradient partial differentiation with respect to the intercept a. Here we are keeping the slope as constant. Dou j by dou a indicate we are we are performing partial differentiation on cost function with respect to the intercept a, keeping the slope as constant. And next we need to calculate dou j by dou b. That means gradient with respect to the slope. Dou j by dou b. Here we are keeping the intercept as the constant. Okay, and these are the after that partial differentiation, this will be the final equation. Dou j by dou a will equal to minus 1 by n sigma is equal to 1 to n yi minus y cap, and dou j by dou b equal to minus 1 by n sigma is equal to 1 to n xi into yi minus y cap. Okay, the derivation for calculating dou j by dou a and dou j by dou b are given here, but now I am not discussing this. If you want, you can go through this. Okay, and this is the final equation, final gradient. Then update the first, next step is to update the parameters. Update the parameters. We want to update the parameters slope and intercept. The intercept a can be updated as a equal to current a value minus alpha into dou j by dou a, and the slope is updated as b equal to current slope minus alpha into dou j by dou b. Okay, and here this alpha is known as learning rate. The dou j by dou a tells how the cost changes when the intercept changes. Then dou j by dou b indicates how the cost changes when the slope changes. Okay, and the gradient descendant repeatedly updates this a and b using this equation in the opposite direction of gradient until we reach the minimum cost. Until we reach the minimum cost, until we reach the convergence, these steps we will be iteratively performed, and alpha is known as learning rate. Then here, what is the significance of the alpha? Learning rate, alpha is known as learning rate. Learning rate determines how much the model parameters are updated in each iteration of gradient descendant. That means here we updated after each iteration, we are updating A and B, right? So how much we will update? It is defined by the learning rate alpha. Okay, and it can be considered as a step size when we walking down a hill towards the lowest point. We can consider it as our step size. Okay, that means learning rate decide how big a step you take in each move, how big your steps. It will be decided by the learning rate. Okay, suppose if the learning rate is too small, like alpha equal to 0.0001, then from the starting position to the minimum position, the steps we performed, we will move in very small updates. There are many iterations in order to reach the minimum point. Why? At each step we are performing very small step, very small increment, very small updations are performed on the parameters. So in order to reach out the minimum value, we require so many iterations, and the convergence will be very slow. Okay, but then what is happening if the learning rate is too large? Suppose alpha is equal to 10, what will happen? That means in each step, in each move, we will take a large step to the downward direction. That time, there is a chance to overshoot the minimum point. That means even if we reach the minimum point, there is a chance to overcome or bypass that minimum point. Again, there is a chance to oscillate between these two sides, and we will not converge anywhere. Never we will converge. So choosing the appropriate learning parameter is a significant theme in linear regression, and it cannot be too small or too large. Okay, then there are several variants for gradient descendant. They are batch gradient descendant, stochastic gradient descendant, and mini batch gradient descendant. In batch gradient descendant, we compute the gradient of the cost function using the entire training data set. For each single step updation, we will use the entire training data set. Then only we will update the steps. But in the case of stochastic gradient descendant, we are using only a single training example at a time. Okay, this will be computationally expensive. Then in mini batch gradient descendant, we will divide the entire training data set into small subset, and each of the subset is called a mini batches. Then from these mini batches, we will randomly select a subset, and using that subset we will compute the gradient and update the parameters. Okay, these are the different variants of gradient descendant algorithms. Then next, here we have different assumptions of linear regression. In order to perform linear regression, we have some assumptions. Like the first one is linearity. There should be a linear relationship between the dependent variable and independent variable. Then only we can accurately use this linear regression. The first two examples are the example first two figures are examples for linear relationship between the x and y, and the third one is the example for non-linear relationship between the x and y. The linear regression can be used if we have the linear relationship between the x and y. And the next one is independence of residuals. The residual means and the difference between the length of the difference between the actual point and the predicted point, right? So these error terms should not be dependent on another one. The dependence mean in the sense that in the case of time series data, we can say that the current value may depending on the previous one, right? But in the case of linear regression, these error there should not be any correlation between these error values, these residual term. There should not follow any kind of patterns. Here you can see from the figure, the first figure, there is no visible pattern. The errors are independent of each other, they are randomly distributed, right? But and the second figure, we can observe there is a pattern like sine wave. So the error terms are dependent. They followed some dependent. For example, in the case of some predictions of ice cream, it may be depending on the climates. Some kind of dependency is there in the errors. So that correlation should be absent, then only the linear regression perform well. And this phenomena, the absence of the correlation between the residual terms, is known as autocorrelation. And the next property is normal distribution of residuals. Here residuals should follow the normal distribution with a mean equal to 0 or close to 0. This is done to check whether the selected line is a line of best fit or not. If the error terms are not normally distributed, there it indicate there are some unusual data point, right? So the one important assumption is that these errors should be normally distributed. This bell curve indicates the normal distribution. Okay, then if it is not normally uniformly distributed, that means we can observe some presence of some unusual data points like outliers or noises. In the presence of outliers, noises, the errors will make some extra values also, or some very small value, or some extremely large values, like that way. So if it is not uniformly distributed, then we can understand that the model is not appropriate for this data set. We'll do something. Okay. And then another assumption is that the equal variance of residuals. Equal variance means the error terms must have a constant variance. And this constant variance is known as homozydicity. This first figure indicates the homozydicity. And if it is spread, if it is show high variance across the spread, across the residuals, this is known as heterozydicity. Then, so usually in linear regression, in order to confirm the absence of outliers or extreme large values, they should follow homozydicity. Okay. Then, as we till now we discussed the simple linear regression. In simple linear regression, we have two variables. We want to predict a variable based on some variable, right? So the variable we want to predict or infer is known as dependent variable, and the another variable we depending on is known as independent variable. And then we want a model that best describe this data, and we try to find out a regression line that best matches these data. And regression can be, multiple regression lines can be drawn, but our aim is to identify the best regression line, the best fit line that correctly model these data points. For that, the measure is to identify or measure the differences between the actual data point and the predicted point. Okay, and our goal is to minimizes the sum of these error values, the differences between the actual data point and predicted data points. And the line can be described by the equation y equal to bx plus a, and b is the slope of the line and a is the intercept. Here the slope indicates how much the y-axis how much the predicted value will change if we perform some changes in the x-axis by 1 unit. How much the house price will change if we increase the house size by 1 unit. That is described by slope of this line, and intercept describes the uh, intercepting point on the y-axis. That means when the x value will be 0, what will be the y value. This is the term intercept. So the regression line will be described by the parameters slope and intercept. Then we want to find out the best regression line, which the parameters b and a of best regression line. That line should be minimizes the error. And for that, we need the cost function, and cost function is mean square. One example for linear regression, and the cost one function is mean square error. Mean square is defined by average of sum of square differences between the actual value and the predicted value. Okay, we take the difference between actual value and the predicted value, then takes the square, then perform the average. Okay, then this is the cost function. Cost function, and then our aim is to identify the b and value with which our cost will be very low. For that, we can use gradient descendant method. Gradient descendant method is an iterative algorithm. It is an optimal algorithm in order to find out the cost function, in order to reach the cost function to the minimum point. Okay, and this is the cost function, which is indicated by the letter j of a comma b, which is equal to 1 by 2 and sigma is equal to 1 to n actual value minus predicted value, the all square. Okay, then objective is to minimize this cost function and identify at what point this what is the value of a and b such that this cost function will be minimum. And the step for gradient and descendant is initialize the value of a and b with some random values, then compute the cost function with this a and b. This is the equation for calculating the cost function. Then after that, we will calculate the gradient, the slope of the cost function. Gradient indicate, the slope indicate what change will occur on the y-axis if we change the x-axis by 1 unit. So we will compute two gradient, dou j by dou a and dou j by dou b. Here we are using the partial differentiation because here we have two parameters a and b. In that cases, we will perform partial differentiation. In dou j by dou a, we are analyzing how the cost j will change, how this cost j will change when the intercept a changes. In that time, the b will be kept as constant. Then the second example, in dou j by dou b, we are analyzing how the cost changes when the slope changes. When the slope changes, how much the cost will change. In that case, the intercept term a will be keeping constant. Then these are the after derivation, after performing the partial differentiation, this will be the equations. Then by using these gradients, we will update the parameters a and b. Okay, then a will be updated by a minus alpha into dou j by dou a, and b will be updated by b minus alpha into dou j by dou a. Here alpha is the learning rate. Okay, then again we will check whether we reach the minimum point. Otherwise we will continue this step. Okay, after updating, using this updated parameter, again we will compute the gradient. Okay, then repeat these steps until we reach the convergence. And the role of alpha learning rate will decide how much, what will be the length of each step at each moment. Okay, if we choose the learning rate too small, it will take lot of time to reach the minimum point from the starting point. From starting to minimum, we will take lot of steps because the length of the steps will be very small, and it will take many iterations. But if we set the learning rate to too large, what will happen? We will, there is a chance to miss the minimum point. We will overshoot the minimum point, and there is a chance to oscillate in between these two sides, and we will never converge. So choosing the appropriate learning rate is very important, and there are several kinds of gradient descendant, and these are the assumptions of linear regression. Next, we will move to multiple linear regression. I think with this we can take a small break, right?
Thank you,
I
ma'am.
can,
It was a great session. So let's have a
we
short
can.
break. By now, we'll be back by 11:15 sharp.
Okay, fine. Thank you.
Okay,
Any
ma'am.
doubt? Anything concerns?
Please come forward and clarify your doubts if you have any.
Okay, let
Okay.
us take the small break. Thank you.
Okay, we'll take the break and come back, ma'am. Thank you.
Okay, okay.
Hello, requesting everyone to come back to your seats. Hope all are back. Shall we begin? Shall we begin,
Yes, yes.
ma'am? Okay, so we are moving towards our second session. And to handle the same, let me invite once again Dr. Jisha Mariam. Ma'am, please. Over to you, ma'am.
Thank you. I hope it is visible, right?
Yes, ma'am.
Thank you. So, in the first section, we discussed about what is machine learning and different machine learning paradigms like supervised, unsupervised, reinforcement, and then semi supervised, right? Then we move to supervised first supervised machine learning techniques like regression. Among regression, we discussed the simple linear regression. In simple linear regression, we are predicting a variable based on another variable. The first figure is the example for simple linear regression. Here we are predicting the salary of the person based on the number of years experienced. Then but the salary of a person not depends not only on the number of working number of years of experience, right? So it may depending on the graduation, their educational qualification, and age. So many factors are there, right? So in that time, we can move to the multiple linear regression. In multiple linear regression, we are predicting a particular variable. We want to infer a variable based on multiple features, multiple properties. Based on multiple properties or multiple features, we are trying to predict the particular variable, right? In this example here, we want to predict the salary of a person based on the education qualification, number of working hours or experience, age of the person. Based on that, we can predict. Okay, it is known as multiple linear regression. And next regression technique is logistic regression. In logistic regression also, we are predicting based on multiple features, but the prediction will be only two classes. We are predicting only whether the person is happy or not based on the education qualification, working experience, age. We can predict whether the person is happy or not. There are only two outcomes, either yes or no, or whether the person is deceased or not, whether the person is happy or not, like that thing. Only two outcomes are possible. But in linear simple linear regression and multiple linear regression, we are predicting some values like such as salary, and in the case of banking examples, it can be the amount of loan we need to pay, like that. We are predicting some quantities, but in logistic regression, we are predicting where only two classes. It can be either yes or no, or happy or sad, like that. Okay. Then then again, coming to multiple linear regression. What are the features influencing a person's salary? It can be the highest level of education, weekly working hours, age, right? Then the variable you want to, one second. Then the variable you want to predict or infer is called dependent variable, just like simple linear regression. And the variable we use for the predictions are called independent variables. And unlike simple linear regression, multiple linear regression can include two or more independent variables. In simple linear regression, we are considering only one independent variable, only one features we are considering. But in multiple linear regression, we can consider multiple independent features, multiple independent variables we can be considered in order to predict a particular variable, and that variable is known as dependent variable. And by considering these multiple features, what impact does that have on the regression equation? Okay, as we know that in simple linear regression, we have the regression line equation y equal to bx plus a, and b is the slope. That means how much if we change the independent variable by one unit, what change will occur on the dependent variable. This is the slope. And intercept a indicate if the what will be the value of y when the dependent variable x becomes 0. Okay, so simple linear regression is modeled by the equation y is equal to bx plus a. And in multiple linear regression, we have more than one independent variables x1, x2, etc., xk. Then how can we model? Just simply y is equal to b1 x1 plus b2 x2 plus etc. bk xk plus a. Here the x1 can be, in the case in our example, salary example, y is the salary we need to predict, and x1 can be the age, x2 can be the working experience, and x3 can be the graduation education qualification, like that. This is a model to represent multiple linear regression. Then what are the assumptions of multiple linear regression? Just like simple linear regression, here also we are assuming that there should exist some linear relationship between the variable x and y. And another assumption is homozygosity. That means the variance of the residual is same for any value of x. It should not be heterozygosity. Then the observations are independent of each other. One feature should not be depending on another. There should not be any correlation. These observations and errors should be independent. Then next is normal distribution, normality. For any fixed value of x, y is normally distributed. Uh, it is also that means if the y values are not uniformly distributed, then it indicates the presence of highly varied data, some kind of outlier, some kind of noises. So usually the data points will be normally distributed. Then multicollinearity. It is a phenomenon where a model with several independent variables. In multiple linear regression, we are considering several independent variable. Okay, in that case we should consider the multicollinearity. We should check the multicollinearity of that model. Multicollinearity means some independent variables are interrelated. And how can we check which of these variables are interrelated? There are two methods, mainly two methods for checking multicollinearity. One is pairwise correlation. In pairwise correlation, we are performing the pairwise, we will select the attributes, features, then we will check the correlation between each of these pairs. Okay, by checking the pairwise correlation between different pairs of independent variables. But it is actually very difficult if we have a large number of independent variables, then taking each pair. That means if we have n features, then we need to take NC2 combination. We need to check NC2 combinations. So checking such kind of checking pairwise correlation will be difficult. So another method is variance inflation factor, VIF, variance inflation factor. It explains the relationship of one independent variable with all other independent variable. That means in pairwise correlation we are considering the each pair's correlation, but but the thing is that one feature cannot accurately describe another feature, but a combination of the features we can a combination of features can describe another feature. In that case, the variance inflation factor is we can consider. Okay, a combination of the features are considered in order to find out the another feature. base using this we can reduces the some features. If a particular combination of features are available, they are highly correlated to this combination is related to another feature, then that feature we can ignore. Okay, then coming to overfitting and underfitting in linear regression. uh, there have always been a situation where a model performs well on the training data. When we creating when we perform the when we try to create a model, we will that model will perform well on our data. But when a new data comes, it may not work well. Okay, that means the model will perform well on the training data but not on the best data. That may be due to the overfitting and underfitting problems. So before that, you can just understand the two terms, bias and the variance. The bias variance trade-off will be discussed in detail, I think, in the tomorrow session. Now, as of now, you can just understand what is bias and what is variance. And bias is the inability of a learning model to capture the true relationship is called a bias. That means it is the inability of the model to capture the true relationship. The high bias means the model is too simple. They are not able to capture the true relationship of the data. That is a high bias model. If the for a model, if the bias is high in the sense that that model is not able to truly capture the relationship in the data. And if the bias is low, means the model is expressive. That means they are able to capture the relationship of the data. That means there are low empirical errors in the data set. Okay, the model is highly identified the patterns. Even the model may try to identify the patterns, including the noises and outliers also. They purely trained or fitted to the given data set. Okay, that is the concept bias when the bias is low. When bias is high means the model is too simple. They are not able to identify the or capture the true relationship in the data. And the variance, coming to variance is the sensitivity of the model toward its training data. That is, it quantifies how much the model will react when the input data is changed. The variance is a measure of the measure to quantify if we change the data, if we made some changes in the data, how the model will react. That will quantified by the quantity variance. Then overfitting. When a model learns every pattern and noises in the data to such an extent, it will affect the model's performance on the future data set. And it is known as overfitting. That means the model learns very well in the available data set, including they identified the patterns, including noises and outliers. But in the unseen future data, they are not able to work well. This is because of the overfitting. The model fits the data so well that it interprets the noise as pattern in the data, because the model fits the data so well in the sense that it considers the noise also as a patterns in the data. When a model has low bias means the model the bias indicates the ability of the model. Inability bias means inability of the model to capture the true relationship, right? So here in this case, or in overfitting, bias will be the low, because the model correctly capture the relationship, including the all the data sets, including all the patterns. And higher variance means the model highly respond even if we change some datas. Even if we change some datas in the data set, model will respond, and that quantity is highly high. So the low bias and higher variance will end up will ends up memorizing the data and causing the overfitting. Low bias and higher weights indicates there is the occurrence of the overfitting of data. Now, overfitting causes the model to become overfitting means the model is more specific to the data rather than generic one. That means in at the time of training time, the model is highly performed, but it shows high training accuracy but very low test accuracy. At the time of testing, there is more errors. So there are several ways to prevent overfitting. They are cross validation that I will discuss. Then if the training data is too small to train, and we can add more relevant data because maybe if the training data is too small, the model will be very simple and it will cause to the low bias. So we can add the data by adding more relevant features, or we can increase the data set size. In that, if the training data is too large, then it also makes some problems. So you can use some feature selection techniques, and we can find out some correlation between the data features. Then you can remove the redundant features. And another way to prevent the overfitting is regularization. So overfitting means at the time of error, at the time of training, the accuracy will be very high, but at the time of testing, it is very low. That means the model becomes more fit to the specific data set, but it will not give more generic result. Then coming to underfitting. When the model fails to learn from the training data set, and is not able to generalize the tested data. In the training itself, they are not able to capture the true relationship. That means here the bias will be high. Okay, bias means the inability of the model to capture the true relationship. If the bias is high, that means model itself failed to learn from the training data sets, and it is also not able to generate the given tested data set. And this type of problem can be easily detected by the performance metrics. And when a model has high bias and low variance, it will cause to the underfitting. Okay, if the model has low bias and high variance, it will be the underfitting problem. And in the reverse, if the model has high bias and low variance, it will leads to generalizing problem with the generalization of the data and causing underfitting, and it is unable to find the hidden underlying patterns in the data. This usually leads to low because this kind of problems, underfitting will leads to low training accuracy and very low test accuracy. In overfitting, we will get high training accuracy but very low test accuracy. In underfitting, we will get low training accuracy and very low test accuracy. And the ways to prevent this underfitting are stated. The different ways to prevent the underfitting are increasing the model complexity by increasing the number of data, number of features, and remove the noises from the data. Okay. Then next, cross validation. As I already said, cross validation is a step to overcome the underfitting, not underfitting, overfitting, right? That means overfitting, the model works well on the training data set, but it fails to work on the test data set, right? Model becomes too specific on the data set. So in order to avoid that, we can perform cross validation. And cross validation is a technique to check how well a machine learning model performs on unseen data while preventing overfitting. Then it can be done by, the first step is splitting the data set into several parts. That means we can split the original data set into training data set and tested data set. And among the training data set, again we can perform the split training set and validation set. Okay, then using these training set, we can model the machine learning algorithm can be worked on this training data set, and we can change the hyperparameters, and the performance of this model can be tested using this validation data set. Okay, then again we can change, if we record we can change the parameters, and we can change some, we can tune the parameters, and we can again using this training set, again we can test the model using this validation data set. Okay, then after completing the model, we can evaluate the performance of this model using the test data set. Okay, this category, this test data set is not used for the modeling of this machine learning model, or modeling of this for the modeling purpose, this data set will not be used. Okay, so in cross validation, it is a technique to check how the model performs on unseen data, because here the test data is the unseen data, while preventing overfitting. For that, what is doing in the cross validation? In cross validation, the original, rather than using the entire data set for creating the model, the data set is divided into two: training data set and test data set. Then from the training data set, we will again perform the division as training data set and validation data set. Then using this training set, we will learn the machine learning model, and that model is validated or tested with the validation data set. And if we record, we can perform the changes in the parameter, we can perform the updations. Okay, then after finalization, the final performance of the model can be estimated using this unseen test data set. These test data set are not used for the any training or validation purposes. Okay, then there are different techniques for cross validation. The one is k-fold cross validation. In k-fold cross validation, that data is partitioned into k non-overlapping subsets. It is divided into different subsets, and each of these subgroups is known as fold. All the data is partitioned. Suppose if we divide all the data into k subgroups, we will have k folds, and each folds will have the size n by k. Okay, n is the number size of the data. Okay, so the entire data set is divided into different subgroups. Then the k-1 groups are used to train the model and validated on the remaining group. Okay, and repeat for all the k choices of held out group. And performance scores from k runs are average. If this k equal to n, this indicates leave one out method. Okay, so in k-fold cross validation, the entire data set is divided into k groups with a size n by k, and one set is used for the validation, and the remaining k-1 is used to train. And the same step will be repeated for the k choices and take the average. Then, as in the previous slide we discussed, when k equal to n, it will becomes leave one out cross validation. That means it is a special case of k-fold cross validation. Here the number of subset equal to number of training data set. That means for each subset, it contains only one data set, one data. Then only one subset is used for the validation in each run. Then in the stratified cross validation, here this is mainly used when the classes are unevenly distributed. In that cases, care should be taken to ensure that each subset should contain the approximately equal distribution of the classes. That means we should ensure that classes are distributed approximately equal in each subset. Each subset should contain the classes equally, and ensure that the individual subsets are representative of the class distribution in the training data set. That means each subset should be a representation for the class distribution for the entire training data set. That means if one subset contains only one category of class, it will not be apt. Okay, so for that the classes should be, each subset should be equally contains all the classes. This is the thing for stratified cross validation. Then coming to regularization is the another method in order to prevent the overfitting. And then when dealing with data set with a large number of features, linear regression can become prone to overfitting. So overfitting occurs when the model fits the training data too closely. That means training error will be very low, and it may even capture the noises. And so what happened? Poor generalization on the new data, because they are too fit to the training data very closely and capturing the noises also, so which will lead to the poor generalization on new data. This is the overfitting concept. Then by the regularization techniques we can reduce this overfitting concept. The one regularization technique is lasso regression, L1. It is also known as L1 regularization. The full form is least absolute shrinkage and selection operator. Actually what happened is, here in lasso regression we add a penalty to the error function as a lambda. We add a lambda parameter to the error function, and this penalty is then multiplied to the sum of absolute values of weights. Okay, here in this in lasso regression we can consider the lambda as a tuning parameter, and this parameter will decide how much we want to penalize the model. This is the equation. That means here the first term measures the prediction error, right? The sum of actual difference, sum of square differences between the actual value and the predicted value. First term we already know. Then the second term penalize the absolute coefficient values. Here the lambda is the parameter, tuning parameter. This lambda determines how strongly the coefficients are constrained. Here these Wj indicate the different coefficients in the linear equations. Weights. Here it is that means b0, b1, b2, that coefficients. Okay, it is considered as a different weights. Okay, so by lambda we will multiply this tuning parameter lambda to the sum of these coefficients. As the lambda increases, these coefficients will be gradually reduced. That means less important features will receive stronger shrinkage. So in that case, some coefficient will reach to the exactly zero value. That way we can reduce the number of features. Zero value coefficients means features are discarded. So no separate feature selection step is needed using this lasso regression technique, and we will get, after applying the lasso regression, we will get more interpretable and compact model. Here what we are doing, we will add or we will multiply the tuning parameter lambda to the sum of the absolute values of the coefficient, right? Then coming to the next regression technique, ridge regression. It is also known as L2 regularization. Here we add a penalty to the error function. This is the error function, and this penalty is the hyperparameter, this lambda, and it is multiplied with the square sum of the absolute values of the weight bj. Here weight is considered as the beta j, and we take the squares, then take the sum, then we will multiply this quantity with the lambda value. Then when we use this ridge regression, ridge regression is used when multicollinearity. That means multicollinearity in the sense there some features are highly correlated. If the correlation of correlation among features are present in the data, that time we can use multicollinearity. Using the multicollinearity, we can reduce the some features, and also it is important when all the features, when it is important to retain all the features in the lasso regression. As the lambda value increases, some features will be reduced. Some coefficient will be reduced to zero, and some features will be neglected. But if it is important to retain all the features, ridge is suitable choice, and it does not fall the coefficient to zero. This is the difference between lasso and ridge regression. Then coming to polynomial regression. As till now we discussed simple linear regression. In simple linear regression, we are considering only two variables. The dependent variable is we are predicting the dependent variable based on one independent variable, right? But coming to multiple linear regression, the model predicts the variable based on multiple features, right? Then what about the polynomial regression? Polynomial regression is a form of linear regression where the relationship between the independent variable x and the dependent variable y is modeled as a nth degree polynomial. In the previous example, our nth degree is 1. Here we are representing it as a polynomial function. Then in linear regression, we are trying to fit the straight line through the data set, right? But here we are trying to fit a polynomial equation. Why we are using this polynomial equation? In order to capture the curves in the data. Straight line we may not be able to capture the curves in the data. So using polynomial equation, we are trying to capture the curves in the data. And the equation for polynomial is y of x comma w is equal to w0 plus w1x plus w2x square plus wm x raised to m. Here m is the degree polynomial, which can be summarized as sigma j is equal to 0 to m wj x raised to j. Here the w0, w1, w2 etc. wm are the regression coefficients, just like b and a. And the polynomial degrees are varying from 1 to 2 to m, right? And through linear, this is an example. Here we are predicting the pressure of the atmosphere using the from the temperature data set. Then in linear regression, we are trying to fit out the a straight line through the data, right? But in polynomial regression, what we are doing, we are actually capturing the curves in this data. In linear regression, we are using the straight line in order to model this data, but in polynomial regression is able to identify the scarce portions in this data. Okay. Then in polynomial regression also, overfitting, there's a chance to happen the overfitting when the model is too complex and fits the training data too closely. So in that case also we can use lasso and ridge regression in order to avoid the overfitting. Then underfitting in polynomial regression, underfitting occurs when the model is too simple. That means if we have no enough data to capture the real patterns in this data, then underfitting may happen. Usually this is happen when we use the low degree polynomial. Then next we are coming to the logistic regression. Then what about the logistic regression? It is also a type of regression analysis in which the outcome variable is binary. That means only two possible values are here. Based on some set of features, we want to predict whether we want to predict the variable which is binary. That means based on the graduation, salary, age, we want to predict whether the human is whether he is happy or sad. This similarly, based on the graduation, work experience, age, whether we are able to predict whether the person is success or failure. Okay. Another example, based on the age, sex, and smoking history, whether the disease is present or not. In these two examples, we can see that the outcome variable is binary value. That means it can take either two value, either yes or no, either success or failure, happy or sad, disease is present or not, like that way. In the previous example, like linear regression, multiple linear regression, polynomial regression, all these cases the outcome is not binary. It can be a real value, right? So it can be the continuous value. But here, coming to logistic regression, the outcome variable is binary. We have only two possible values. For example, from the age, this is the data which consists of the features age, gender, and smoker status. Using this data, we are able to predict whether the disease is present or not. This 1 indicate the disease is present and 0 indicate disease is not present. Then in this case, why do we need logistic regression? Why can't we use linear regression in this case? In linear regression, what we are actually trying to do, dependent variable is predicted as the equation b1 x1 plus b2 x2 plus etc bk xk plus a. Here x1, x2, etc xk are the independent variables, and b1, b2, a are known as co-regression coefficient, right? We are trying to fit out a straight line with the equation y cap equal to b1 x1 plus b2 x2 plus etc bk xk plus a, right? Then now the dependent variable y cap is binary, right? So linear regression would simply put a straight line through the point, right? See, here we have the output variable. On the x-axis, we will draw the independent variables. On the y-axis, we will draw the dependent variable, right? On the x-axis, we will draw the independent variables such as working hours, age, like that way. And on the y-axis, we are drawing the the variable we want to predict, like dependent variable. In logistic regression, in our current example, we have only two values, either 0 or 1, either sad or happy, either disease is present or not, like that way. But and the points will be looks like this, right? The points can be either in 0 or in 1, right? So in linear regression would simply put a straight line through these points. Then do you think it is correct? Fitting a straight line through this point is correct? Of course, no, right? Then goal of logistic regression is to estimate the probability of occurrence. That means the value range for the prediction should be in between 0 and 1. So we need a function that takes only the values in between 0 and 1, and that is for that we can use the logistic function. See, this is a function, logistic function. It is not a sigmoid function. It this have the S-shaped curve. Then here and this function is represented by f of z is equal to 1 by 1 plus e raised to minus z. And this is the logistic function we can use, and it is not a sigmoid function. Then, and the properties of these functions are the output will be in between 0 and 1. So that means any real numbers is converted into the probability, and this curve has S-shaped curve. And large value indicate the probability closest to 1, and the smaller value indicate the probability closest to 0. Okay, and the 0 value at the 0 point, it will be, the probability will be 0.5. Okay, then for Z, the equation for linear regression is simply used. What actually this is the function for logistic function 1 by 1 plus e raised to minus z. Then in this case, in the place of z, we are just putting the equation of linear regression. What is the equation for linear regression? Y cap is equal to b1 x1 plus b2 x2 plus etc. bk xk plus a. Okay, then we are trying to finding out that probability that the dependent variable y becomes 2 or dependent variable becomes 1 given that the specific set of independent variable, right? Here we are trying to find out the probability that the dependent variable becomes 1 given that this vertical line indicates given that the specific values of independent variable. With these specific values of independent variable, what is the probability that the dependent variable y becomes 1? Clear? With these specific values of independent variable, what is the probability that the dependent variable y becomes 1? And it can be calculated by 1 by 1 plus e raised to minus in the minus z. In the case of z, we can simply put the equation for linear regression like b1 x1 plus b2 x2 plus bk xk plus a. Okay, and this quantity will give the probability that with the given specific values of the independent variable, what is the probability that this y becomes or this y takes the value 1. Okay, then in our example, this equation will gives that what is the probability that the given person is deceased or the given person have a certain disease with a given set of with a particular specific values of age, gender, smoker status. Okay, this probability will give the idea about what is the probability that the given the person with a particular age, particular gender, particular smoking status, what is the probability that that person have a certain disease. And it can be calculated using the logistic function 1 by 1 plus e raised to minus B1 age, B2 male, B3 smoker plus A. And B1, B2, B3 are the regression coefficients, and age, male, smoker are the independent variables we use to predict the output. And A is the intercept term. It is also known as regression coefficient. Okay, then and then, of course, as in the linear regression, our next aim is to identify these coefficients, right? The coefficient that best fits our data. And so, we need to find out the value of B1, B2, B3, A, which determines or which that best fits this given data. And for that, we can use maximum likelihood estimation. Okay, this equation will give if you want to calculate the probability that the given person have deceased or not with the specific values for the independent features such as age, male, smoker. We need to find out the coefficient, regression coefficients B1, B2, B3, etc. that best fit this given data. For that, we can use maximum likelihood estimation. So, coming to maximum likelihood estimation, for the given data point xi, we can represent that for the given data point xi, that includes particular values of age, smoker, sex. Okay, with this data, what is the probability that this data point belongs to the class 1? And it is represented by y cap. Okay, first of all, we have the data point xi, which have a specific value for the sex, smoking status, age, and with this data, what is the probability that this person belongs to the class 1, and it is represented by the y cap, where this y cap is modeled by the equation 1 by 1 plus e raised to minus zi, and zi is the linear regression model with the equation b0 plus b1 xi1 plus b2 xi3 plus bn xin. Okay, then here in this case, we have in logistic regression we have only two classes, right? So the probability of the data point xi with a particular set of feature values, what is the probability that that point will be, that person will be belongs to the class 0? It is represented by probability of ya given ya equal to 0 given xi is equal to 1 minus ya cap. Ya cap, what is the ya cap? Ya cap is the probability that the given point xi with the specific values of features belongs to class 1. Okay, then in order to calculate the probability that the given data point xi with the specific features belong to class 0 can be determined by just simply subtracting this yi value from 1, because the sum of probability values will be 1. So just here we have only two classes, so just subtracting from 1 minus ya cap. Then for the simplification purpose, these two equations we can combine. We can combine both the cases into one equation, like P of ya given xi is equal to ya prediction raised to ya into 1 minus ya cap raised to 1 minus ya. This is why, because in case 1, when ya becomes 1, just simply putting the 1 in the place of ya, then we will get ya cap, similar to the equation in the left side. Then when ya becomes 0, then put this 0 in the place of ya in this equation, then we will get 1 minus ya cap. So this both formula we can combine into the single one, and it works well for these two classes. Here yi is the class label for the ith sample, and xi is the all input features of the ith sample. Then likelihood function. Then here assuming in logistic regression, one assumption is that all the observations are independent. Okay, then in that way the likelihood function can be defined as product of these terms. The previous one we combine the probabilities, right? So product of these probabilities can be used to compute the likelihood. Here where the theta is the different parameters in our linear regression equation b0 b1 b2 etc bn, right? Yeah, is the theta, we want to find out the likelihood as a function of theta, where theta is a set of b1 b2 b3 etc, and these are the different coefficient, right? So we want to find out these coefficient that best fit this data. For that we can find out that we can use the likelihood. In likelihood, what we are doing, we are assuming that the observations are independent, and so that we are taking the product of each of the product of probabilities of each of these observations, and theta is the feature vector b0 b1 b2, our coefficients. Okay, then our goal is, then with this equation, what it indicates, the likelihood is a function of the model parameters theta, which is equal to b0 b1 b2 etc bn, and different values of theta, that means different values of b0 b1 b2 etc will give different probability values. So we want to get the values of b1 b2 b3 such that it looks like the exact data values. It should be likely to the exact values. So our objective is to maximize the likelihood of these data points. That means objective is maximize the theta of L of theta and find the parameters b0, b1, etc. bn that makes the observed training data most likely. And this function is known as likelihood function, and our objective or goal is to maximize this likelihood function and and find out the parameters in that maximum likelihood point, such that while maximizing this likelihood we will get the observed data most likely. Our errors will be less. Then next we will take the logarithm on both sides. This is the equation or likelihood function. Then we will take the log on both sides, log L of theta and log pi I is equal to 1 to n ya cap raised to ya into 1 minus ya raised to 1 minus ya. Using the equation log ab equal to log a plus log b. Right? So this equation will be converted to, this is a product, right? Product of different terms. So it will be converted to the sum terms. This log is taken for the easily computation. For the ease of the computation, we are taking the log on both sides. Then after applying log, we can consider, instead of product, we can consider as a summation terms. Okay, and finally we can call this function as log likelihood. Okay, then as of now our aim is to maximize the log likelihood, and find out the parameters of that type, right? Then so machine learning algorithm usually reduces the cost function. In most of the algorithm, our aim is to reduce the cost function. So convert this maximization problem into the minimization problem. For that we can take negative on log likelihood. Okay, just take the negative values on both sides. Then in order to then take the average value by dividing n. Then the final cost function will be look like minus 1 by n, sigma is equal to 1 to n, the sum of these terms. Okay, then our objective is to minimize this cost function. And this cost function is known as cross entropy loss, log loss function. And at that particular function, at that particular minimum function, we can find out the values of regression parameters. Okay, then in order to find out the minimum value, again we can perform the gradients. We find that means we will change the we will compute the gradients after finding out the cost function. Here the cost function is cross entropy loss function. After computing the cost function, we will compute the gradient with respect to the parameter bj. Here we have multiple features, so multiple b values are available. So for each bj we will compute the gradient. That means what change, if we change the feature bj by 1 unit, then what change will occur in the cost function, that is indicated by dou j by dou bj. Clear? Then here I did not describe the derivation of partial differentiation. Here we used a partial differentiation because multiple variables are there. So we are changing only one variable and keeping all other variables as constant. Then for the intercept term also, we are calculating the gradient dou j by dou b0. Here b0 is the intercept term. Then b0 is changing by 1 unit. Then analyzing what change, if we increase the intercept term by 1 unit, then what change will occur in the cost. Okay, so the both gradient dou j by dou bj and dou j by dou b0 are evaluated. Then next, after calculating the gradient, The next step is to update the parameters. Update each parameter by the equation new parameter bj is equal to the current parameter bj minus alpha into dou j by dou bj. Here alpha is the learning rate and bj is the current parameter value, and this learning rate will decide the change in the how much we take the steps. As in the linear regression, this learning rate will decide how much we take the steps at each move. Okay, this is also similar to the linear regression model. Okay, this is about the regression. Firstly, we start with simple linear regression. Here we have only two variables. Then we try to find out or fit the data using a regression line. We can draw multiple regression line, but we want to find out the best fit line. For that, our aim is to reduce the sum of these errors. This red line, the difference between the actual point and data point, is considered as the error. Then our aim is to reduce, goal is to find the regression line that minimizes the error. And the regression line can be modeled by the equation y equal to bx plus a. B indicate the slope and a indicate the intercept. The slope means how much the if we change the how independent variable by 1 unit, then what change will happen in the independent variable. This is a slope, and intercept is the point on the y-axis when the independent variable becomes 0. Then using mathematical calculations, we can compute the values of slope and intercept, but our aim is to minimize the error. We have a cost function and minimize this cost function and identify the parameter that satisfies this minimum cost function. So goal is to find out the regression line that minimizes this error. That means identify the best fit line, and residual is the difference between this actual point and the predicted point. It can be the residual equal to 0 means the model fits correctly, perfectly, and the positive value indicates the model underestimates the actual data, and negative value indicate model overestimate the actual data. Then here our cost function can be mean squared error, which is the average of squared sum of differences between the actual value and predicted value. And this mean square error will always be a non-negative value, and the square due to the squaring we will get larger errors are more penalized, and lower mean square error indicates better model performance. And our objective is to find out the slope and intercept for the best fit line. For that, we can use the gradient descendant function that reduces the cost function as minimum. This is the this is the cost function, and our objective is to minimize this cost function j of a comma b. And you see, for that we used the gradient descendant. At each gradient descendant, we starts with a random values of a and b, random parameter values we will start, then compute the cost function with this random b and a, then calculate the gradient dou j by dou a and dou j by dou b. After that, we will update the parameters a and b as a minus alpha into dou j by dou a and b minus alpha into dou j by dou b. Here alpha is the learning rate. Depending on the alpha, the model's performance will vary. If alpha is too small, at each step, at each move, we will take small step. So there are too many iterations and slow convergence. But if alpha is too large, there's a chance to overshoot the minimum value, and there is a chance for the oscillation in between these two sides and never converge. And there are several variants of gradient descendant. And the main assumptions of linear regressions are linearity between the features, independence of the errors, normal distributions of the errors, homozygosity, and then coming to multiple linear regression. Here the predicted variable, the variable we want to predict or infer will be depending on multiple features rather than single feature. And similar to single linear regression, it can be again represented by the multiple, based on the multiple independent variable like y is equal to b1 x1 plus b2 x2 plus etc bk xk plus a, and x1 x2 xk are the independent variables, b1 b2 bk a are the regression coefficient. Here also we have different assumptions, and multicollinearity means it is a phenomena that different variables, different features are interrelated, and we can this interrelationship can be found out, can be find using pairwise correlation. And another one is variance inflation vector. In variance inflation vector, we used a set of features in order to predict another feature, in order to find out the relationship of another feature. And then we move to overfitting and underfitting. And also we have the two terms, bias and variance. Bias means inability of the model to capture true relationship, and variance is the sensitivity of the model towards the training data. And overfitting means the model becomes too specific rather than generic one. That means in overfitting cases, the training accuracy will be very high, but it will be the testing accuracy will be very low, and this will be due to the low bias and higher variance of the model. And the overfitting can be avoided using different techniques like cross validation, regularization, by increasing relevant, more cleaned data. If the training data is too large, we can reduce the data features by feature selection techniques. And in underfitting, where model fails to learn from the training data itself, and also it is not able to generalize the test data, it is known as underfitting. In that case, we will have the model will have high bias and low variance. This is mainly because of the data is too simple, and so we can avoid the underfitting by increasing the model complexity. And one way to avoid the overfitting is cross validation. In cross validation, we are splitting the entire data set into two sets, training set and test set. Then among training set, and usually the normal proportion for training and test split will be the 70% for training and 30% for test. Otherwise, you can use 80% for training and 20% for test set. And again, the training set can be again classified for training and validation. Using this training data set, the model will be performed and tuned the parameters. And then after the model creation, the final performance will be evaluated based on the tested data set, which will be the unseen data for the model creation. And different cross validation techniques: k-fold cross validation, leave one out cross validation, and stratified cross validation. And next is regularization. It is a technique to avoid the overfitting. Here we have L1 regularization, lasso regression, and ridge regression, L2 regression. In both cases, we have added some tuning parameters to the weights or weight parameters. Then coming to polynomial regression. In linear regression, we are trying to fit out the straight line. But in polynomial regression, we are trying to find out, or we are trying to tune the data, curve of these data. And then coming to logistic regression. In logistic regression, the outcome will be either outcome is binary. That means we have only two classes, either yes or no, success or failure, disease is present or not, like that way. Then in logistic regression, we used the function, logistic function f of s is equal to 1 by 1 plus e raised to minus z, and the z value is the equation for linear regression. We will put that, and we will use, in order to find out these coefficients that best fit this data, we can use the maximum likelihood estimation. This is the function for likelihood in the logistic regression. And then our aim is to, our objective is to maximize these likelihood data, maximize this likelihood function, so that we can find out the parameters that makes the observed data most likely. Then for the mathematics of the mathematical computation, we took the log on both sides, because after taking log, this product term will be converted to summation terms. Then as machine learning algorithm usually minimizes the cost function, we want to convert this maximization problem into minimization problem. Then for that, we took a negative value on both sides, on both side of log likelihood function. Then it becomes gross entropy loss function. Then similar to gradient descendant, in linear regression, we compute the gradient. That means we perform the partial differentiation for each parameters. Then after computing the gradient, we will update the parameters as bj is equal to bj minus alpha into rho j by rho bj, and alpha is the learning rate. This is the thing for regression. Then in the afternoon section, we can start with the classification algorithms. Till now, we discussed about different.
Okay, ma'am. Thank you. Ma'am, someone has posted one question in the chat box, ma'am.
Yeah. Lasso and ridge, it is both are regularization technique. The main difference is in lasso, we are actually adding the parameter, tuning parameter lambda, and it is multiplied to the sum of just weight function. So if what happened actually is, but in the case of ridge regression, this lambda parameter is multiplied with the square of weight parameters. So in lasso, what is happening? There is a chance to reduce some features into the zero. There is a chance to neglect some features. But if we want to keep all the features, then you can go with ridge regression. Actually, I have a plan to show this in the hands-on session, lasso and ridge regression.
Okay.
That time, I think you will get the clear idea.
Okay. Thank you, ma'am.
Thank you, ma'am. That was a really insightful session. I hope the session provided a clear understanding of regression in machine learning concept to everyone. As we conclude the morning session, now we are going for a lunch break. The afternoon session will resume at 1:30 p.m. Kindly be back few minutes before the schedule. Thank you.
Thank you.
Thank you, everyone.